before before I address the homework problem, I want to give you an example. And that sort of. So in this problem, we'll have an acceleration of a moving particle, and we want to find the velocity and the position function. And to do so, we need to have some initial. We need to have some information about the initial condition, such as what is the acceleration. What is the velocity and what is the position at time at the given time. In this case, we'll pick up the initial velocity and initial position. So we'll have data at t equals 0. Okay. So here's the information about this in this problem. We have the acceleration of a moving particle. It's okay. Is given by the following: a of t equal, and this is a vector, 40I plus 60j plus k. The initial velocity and initial position are v at 0 is I minus j plus k, and the r at 0 is simply I. Okay? And what we need to do is find the velocity and the position, the particle's velocity and position. Vector functions. We all set?
No, I need the rubber bands a little bit tighter because it's not holding the camera on.
But she's already.
Brittany is connected right now. Can you hear us, Brittany?
Yes, I can hear fine.
Okay, Brittany, good. And everybody can see Brittany.
Do you want it pointed toward everybody?
No, it's okay. You guys, I can hear her, and she dressed nicely?
Yeah, Brittany's always dressed up.
All right. So here's the solution. I'll continue, Brittany. The camera is, for some reason, let me turn it here.
Oh, that helped a lot.
All right. So the velocity is the integral of the acceleration. Okay, as the acceleration is the derivative of the velocity. So here we need to integrate this particular function. So we integrate 40I plus 60j plus k, and the result will be 4t squared over 2. So 2t squared in the I direction, 3t squared in the j direction, and t in the k direction. But we do have the vector constant c1, and because this is indefinite integration so far. And how we find the value of c1? Well, we look at the initial condition, and when t equals 0, then all the I, j, k terms disappeared. So the only remaining, the only surviving term is the constant vector. But also we are given that the initial condition, the initial velocity is I minus j plus k. So we have now an expression for c1, and now we can include that in our solution for the vector v, and we'll see the I terms. We have 2t squared plus the I from here. So 2t squared plus 1 in the I direction. In the j direction, we have 3t squared minus 1. And in the k direction, we have t plus 1. So we accomplish the first part of the assignment. And now, Robin, you see the resemblance, somewhat resemblance between what we are doing now and that particular Drury homework problem. That has a little another hitch to it. But let's do the second part. Well, the position is the integral of the velocity, as the velocity is the derivative of the position. So we need to integrate this thing, and as we integrate it term by term. So what we end up having is, let's see, 2t squared, the integral of 2t squared plus 1 will be 2/3 t cubed plus t, and that will be in the I direction. The integral of 3t squared minus 1 will be simply t cubed minus t in the j direction, and the k produce t squared over 2 plus t, like so. And then we have plus the position, the constant vector c2. So again, we'll go and replace t with 0, and notice that all the ijk terms contain t, so they disappear. They all zero out, and what's left is c2. And this, we are told that it's equal to I. Okay? So again, c2 equals I, and now we can complete the assignment and say that the vector, the position vector r of t, is 2/3 t. This has to be t cubed. I think I said t cubed and I wrote t squared for some reason. This is the I component. I'm sorry, we need to add 1 for the constant vector. So 2/3 t cubed plus t plus 1 from c2 in the I direction. The rest does not change. So we have, for the j, we have t cubed minus t, and for the k, we have t squared over 2 plus t, like so. And these conclude this particular example.